Lenz's law 3. A small region of magnetic field is enclosed within a larger conducting loop as shown. If the magnetic field is increasing into the page, underline that, in which direction is there an induced EMF in the outer loop, an induced current in the outer loop? Lenz's law says that if we have a magnetic field directed into the page and it's increasing, Lenz's law says, I don't like change. I don't like that it's increasing. So I'm going to fight that with my thumb. If it's increasing into the page, then we're going to fight it with our thumb. And which way is the induced EMF? And the induced current, we're going to go counterclockwise. How is it possible that the outer loop knows that an induced EMF should be brought into being at the location of the outer loop? In other words, what could be sent out in all directions when a magnetic field is changing? When the magnetic flux is changing, basically light is emitted. And the rate at which the field is changing, the rate at which the flux is changing, determines the light's frequency and its wavelength and so on. But basically, you might have wondered, hey, I'm okay with doing this, doing Lenz's law, but how does this outer loop know that something funny is going on in the middle? It's because light is being emitted. Let's try one more problem here. In the loop shown, no magnetic field is present initially. In the figure to the right of the first, the same loop is shown 0.14 seconds later when the magnetic field has increased at a uniform rate to a value of 4 teslas. The loop has a radius of 6 centimeters. In which direction is there a current induced? Well, let's think here. Initially, through the loop, no magnetic field. Suddenly, into the page. I'm going to fight that. I don't like that change going into the page. That's what Lenz's law says. Counterclockwise. And what's the magnitude of the induced EMF in the loop? We're going to have to use Faraday's law, which says that the magnitude of the induced EMF is numerically equal to the rate at which the magnetic flux changes. And as we've said many times before, let me put the ddt right there, magnetic flux is essentially B times A. And if A isn't changing, then we can just write that on the outside, and then we can just say, oh, well, dB dt. So let's do this. What's the area of this thing? The area is going to be pi times r squared, and what's r? It's 6 centimeters. I'm going to just change that into meters real quick. And then at what rate is the magnetic field changing? It ends at 4 teslas, and it started at 0, and the amount of time that has elapsed, you see, is 0.14 seconds. So this is going to give us the magnitude of the induced EMF. I think a calculator would be handy for this, and when I put this into my calculator, I got a value of 0.32. And what's the unit for EMF? It's a voltage, so volts.